Our next speaker is Puneet Gupta. Puneet received his BTech in electrical engineering from IIT Delhi in 2000 and a PhD from UCLA in 2007. He's currently a faculty member with the Electrical and Computer Engineering Department at UCLA. He co-founded Blaze DFM in Sunnyvale in 2004 and served as its product architect until 2007. He has authored over 170 papers, has 18 US patents, a book, and a book chapter in the area of design technology co-optimization, as well as variability, reliability aware architectures. He's a recipient of the NSF Career Award, the ACM SIGDA Outstanding New Faculty Award, the SRC Inventor Recognition Award, and the IBM Faculty Award. He's led multi-university impact center, which focuses on semiconductor technologies. With that, Puneet, you're up.
Thanks, Ravi. Just a minor correction. My PhD was at UC San Diego, not UCLA. But that's
okay.
That's okay. I'm going to talk about two things mainly. First, one thing I'm going to talk about is kind of some little bit economics of disaggregating SoCs into chiplets. And we have heard kind of that kind of argument in the past almost 2 hours, multiple ways, multiple times. So there's another kind of variant of that pitch. I'll focus most of my talk on our recent experience trying to design a massive chiplet-based system and the challenges we faced, and at least one solution to those challenges. And depending on how much time we have left towards the end, I will essentially talk briefly about what do we want from these 2.5D substrates in the future in terms of their technological properties. So let's start. I'll start the talk with a result plot itself. So this is some work we had done a couple of years back of just looking at a relatively simple chiplet-based system where you have a processor and its last level cache, NSRAM, separated into chiplets. And what we were trying to look at is if I have multiple product lines of this generic processor, each serving a different market segment, can I share these chiplets to reduce the total chiplet ecosystem costs? And if I'm able to do this, what do I gain? So let's first look at the positive side of the story, which is if in an ideal world, I could assemble processor systems using chiplets, then what it buys me is an immense degree of relatively cheap customization, right? Rather than trying to respin an SoC for every small application segment, I can respin a chiplet system by integrating or kind of cutting and pasting different chiplets together. How much can I gain potentially by doing this? So these are just three classes of workloads. So if you look at it this way, the spec is kind of the conventional kind of call it desktop workstation style workload. EMBC is kind of a more embedded style workload. Splash NPB is, for lack of a better word, call it server class workloads. And typically you would imagine that each of these segments would be served by multiple product lines and completely different product lines. And what we were looking to see is that by assembling chiplet systems together with a huge variety of chiplets available, how much could you gain? And the idea, what we found is you could gain up to a factor of 2 under performance or energy delay product type metrics if there is an infinite variety of chiplets available, right? So that's a motivation of why would you even want to go to chiplet approach. One of the motivators besides the cost and heterogeneity angle is it allows for low cost system customization. Okay, so now something happens. Anyway, so we also looked at this in the same context of the same system. We also looked at the typical cost argument. And on the left side, you see this plot of showing the same system, the processor plus cache system, scaled multiple ways. So if I have a 1x system to all the way up to an 8x system, basically larger number of processor cores, bigger corresponding cache, et cetera. And the conclusions are somewhat obvious. The first conclusion is that the cost benefits in context of chiplets mostly exist in large systems. Small chiplets, small SoCs don't really benefit from disaggregating, right? And what qualifies as large obviously depends on technology maturity, essentially the underlying yield of the chiplets, and also on integration costs. These numbers are generating, assuming our best effort guesses on integration costs. Those are not usually publicly available, but the general conclusion holds. If you look at this right plot, it is making a slightly different observation. Is now let's imagine that I do have a chiplet ecosystem, right? And it's not, and if so, how many chiplets do I need in that quote unquote ecosystem for the simple system, processor plus cache, to not suffer a performance hit or an energy delay product hit compared to the corresponding SoC? And if we are not willing to suffer any performance hit, the sheer number of chiplet variety needed would be massive. It's just, I mean, any argument for chiplets kind of just goes away flat right there. So every single time you disaggregate, you should, and you want to realize a cost benefit, especially over reuse of chiplets, you should expect to lose out something, right? And if you don't expect to lose out anything, then I mean, there is like no point to it. Okay, so that was the second side observation that we made. So that was a very, very quick kind of segue. I want to segue into our experience designing a large chiplet-based system. So unless there are any quick questions here, I'll move on.
Puneet, I do have a question on your previous slide.
Okay.
Now that you know you are going to disaggregate in chiplets, why do you not build something that will beat SoC performance by taking advantage of your possibility to integrate? Like, why live with that?
Oh no, this is assuming that. So I skipped over some in between slides for the interest of time. What we did here was we assumed that you have processor microarchitectures, a huge variety of them available. You have SRAM caches in all possible sizes and multiple technology nodes available as a universe of pool of chiplets that you could select from. And then there's an optimization loop which figures out what is the total ecosystem cost, how do I minimize it? Because my cost, design cost, verification cost increases with sheer number of chiplets I need to sustain. And accounting for that, this is what we get.
Got it. Thank you.
Versus if I had a custom SoC per application segment. Okay, let me move on to our experience designing this large chiplet-based system. I'll be kind of a little bit brief on this. Detailed paper is going to appear in DAC later this year. So what we've been looking at wafer scale integration for a couple of years, and about 1.5 to 2 years back, we started looking into building a system, a wafer scale system, a processor type wafer scale system. And why do we want to do that? Because chiplets, the first one interesting thing that it offers us is it offers high density interconnects between neighboring chiplets rather than going out of the package. And second, it can allow us for large amount of computation as well as memory capacity because of the scale. So the approach in so-called wafer scale integration here is I take a passive wafer with only interconnects, couple it up with, let's say, known good chiplets. Yes, the previous talk raised the issues of what known good even means, but I'll briefly talk about that. And build this, bond these quote unquote known good chiplets onto this passive interconnect wafer and assemble a large system. Okay. So that's the context here. Our initial attempt is around building a 100 millimeter wafer scale system, but the approach spans all the way to even 300 millimeter wafer scale systems. The underlying bonding and packaging technology, I'll not go into the details. My collaborator, Subbu Iyer, I mean, I'm sure he has talked about this multiple times on this and other packaging forums. But I'll very be brief about it. This is based on copper to copper bonding and with 10 micron IO pitches and 2 to 4 micron wire pitches and inter-die separation of about 100 microns. Those are typical kind of technology characteristics of this integration technology. Okay, let me move on. Okay, and this is just to illustrate that we have done a bunch of simple prototypes to just demonstrate bonding yield, patterning yield, etc., etc. So what are we building, or what are we building? we are building a 2000 chiplet or 2048 chiplet architecture to be exact. The chiplets themselves are in a commercial 40 nanometer technology. There are a total of 2048 chiplets, about 1024 processor chiplets, and 1024 memory or SRAM chiplets in this case. Each processor chiplet has 14 ARM cores, and then within some networking aspect to it within the chiplet and chiplet to chiplet network. And these are the exact details, and you can see that the shared memory bandwidth, network bandwidth is pretty high. And this is for a 100 millimeter wafer scale system, or maybe a little bit larger. Total area is about 15,100 millimeter. The peak power for the system, I estimate, because we are using somewhat lower power ARM cores, is about 700 to 800 watts. And this number is important to understand our design choices coming in the future. If this number was 7 kilowatt, we wouldn't have made those same design choices, obviously. So what are the challenges that we face when designing the system? First, how do we deliver power to such a large substrate? How do we deliver power to such a large substrate? How do we reliably distribute clock to such a large substrate? How do I test such a large substrate? Some of the this problem was hinted at in the previous talk as well. And finally, given the fact that even if we try our level best to get quote unquote known good die, we will never get them. What is at least some fault tolerance strategy? In our case, the fault tolerance strategy was primarily focused on the network, essentially to allow us to bypass faulty chips. And the assumption was that we have enough number of these chips, 1,000 of them, that even if we lose a few, overall performance metrics are not really going to matter as much. So with that. So how did we deliver power on this? What we decided, at least for this run, was to deliver power from the edges of the wafer. Now, this may sound a little bit weird because you will get tons of losses going into the center of the wafer. But I completely agree, it's very wasteful, but it is very simple. Your power coming from the edge of the wafer through conventional wire bonds, and you get losses, but because of power consumption, overall chip power consumption about 700 to 800 watts, the losses are not horrible. Let's put it that way. You deliver at 2.5 volts, and all you need to make sure is even with the losses, by the time you get to the middle of the wafer, the voltage that is reaching there is upwards of what is the technology voltage, which in case is about 1 to 1.1 volts. As long as you can ensure that, at least things would be functional. And then, of course, there's a regulator sitting on every die. It's a simple LDO to do the down conversion. So yes, you have absolute right to complain that this is a wasteful strategy, but it's a very simple strategy. Other approaches we have looked at from front side or back side power delivery, but they are more complicated and definitely more worth it for higher power systems. Other small thing I wanted to point out is, remember, in this substrate, in the first run, we did not have access to any sort of deep trench caps in the substrate. So as a result, all the on-chip decoupling, all the decoupling cap had to be on-chip, which means a big fraction of our chiplets were just decap banks. And this is just showing you the die photo of that. Now, for clocking is also interesting because there are two issues we have to face. One is clock generation itself. Now, in a conventional small scale system, chiplet or otherwise, you can put a PLL there. You can supply a stable reference voltage and a master clock relatively easily for PLL to lock and generate a clock for you locally. On such a large substrate, providing a stable reference voltage all across the wafer is hard. So the approach we decided was that we will supply that reference voltage only to one or few chiplets towards the edge of the wafer where the PLLs would be activated. That will generate the high-speed clock. And instead of distributing a low-speed clock everywhere and having a PLL generate the high-speed clock locally, we distributed high-speed clock everywhere. And we did the math that the extra power losses are essentially negligible. So we distribute a fast clock all over the wafer. Other small tricks we play is if you imagine a clock distribution network which is spanning tens of millimeters, another problem that you run into is duty cycle distortion. That you have huge chain of inverters or buffers, clock buffers, and because of variability issues, slowly the clock gets distorted and eventually vanishes. On large SoCs, this problem is also there. It's just that in our case, this problem happens on steroids. So the simple solution that we did for this, we had a couple of tricks, but the main solution was that at every chiplet boundary, we inverted the clock. So neighboring chiplets are operating in opposite phases of the clock, and the distribution and the network interfaces are all asynchronous. One more thing that we did to account for some chiplets failing for whatever reason is there's fault tolerance in the clock distribution network itself. So there is every chiplet can source its clock from any of its 4 neighbors, depending on which one is active. And it just detects automatically which clock is still functional and uses that internally and forwards it further, just to have fault tolerance in the clock. Because if clock dies, the whole system dies. So you have to ensure clock and power absolutely reach everywhere. Okay. Test. This was hinted again in the previous slide, and the approaches are not new. We are essentially using some of the approaches that were highlighted in the previous talk itself. So for pre-bond die testing, we had large sacrificial pads which could be probed, relatively small number of them, and then the actual signaling and pads, etc., are much smaller. So the signaling pads at the bottom, you can see in this orange circle, these are at 10 micron pitch. These are the probing pads are much larger. I mean, yeah, they are thought to be probed using standard probing methods. But the sacrificial pads are not bonded. They are truly sacrificial. But this allows us to test the bare die before bonding or debugging purposes, etc. Post-bond, again, this was hinted in the last talk. Sorry, some of it is a repetition. That we had to solve 2 issues. One is we just have too big of a substrate. So even conventional JTAG type schemes, we do not want to have a single JTAG chain stitching together 1,000 chiplets. So we just broke it up into multiple independent JTAG chains. This gives a slight amount of fault tolerance, as well as makes the test and loading time manageable. If you had one chain, I mean, it'll take us 2 hours to just run through a single JTAG test to load the memories. So that was just, so we had 32 total independent JTAG chains. The second aspect was this chaining or progressive unrolling, which is also, I think, part of the IEEE 1838 standard, or at least the proposal of the standard, which is we have essentially a loop back from every tile in the JTAG interface. So you could test and unroll specific parts of the chain to diagnose where the fault happened, piece by piece. Okay. The last bit is a little bit about fault tolerance. I mean, there's a lot more stuff on fault tolerance that was in the chip, but I want to highlight just one aspect, which is a big part of our fault tolerance comes from a fault tolerant network in this design. So our primary approach is we have 1,000 of these tiles available, which are essentially doing the same thing. So the easiest and most flexible fault tolerance we could think of is if a few number of them fail, we want to be able to bypass them and let the rest of it work. So that basically means the clock should be able to go everywhere, power should be able to go everywhere, and in the network, we should be able to go everywhere if a certain network node essentially stops working. And here what we did was by simple network resiliency tricks. So we did, what we do is a dimension order routing, but have 2 parallel networks reaching to the between the same connections. And this allows us to not lose, I mean, this is just showing you on the right, the plot that the red curve is the conventional dimension order routing, where if number of faulty tiles on the small, in this 1,000 tile system, even if it reaches to up to 5 or so, you lose 12% of the wafer, which is inaccessible at this point. We can bring it down to maybe about 1 to 2% of the wafer by doing this redundant routing. Okay. IOs, the main challenge that we faced were our IOs were 10 microns pitch, and the depth was about 20 micron. And since our interdie distance was just about 100 micron, we really did not need SerDes or any more sophisticated thing. These were essentially cascaded buffers. And therefore, the energy per bit for data transmission was about 0.1 picojoules per bit. Just for bonding yield redundancy reasons, we had 2 pillars per IO. We had ample space for it, so there was no downside to it. The entire IO cell had to fit in this 10 by 20 space, which was a little bit of a challenge given that we wanted to have at least some basic ESD protection on this. So these are ESD diodes, buffer, everything needs to fit in this small space. And this, for small IO chiplet connection, this probably is going to remain a challenge of how to accommodate enough ESD protection within that small IO area. Okay. So where we are right now, the chiplets are back. The chiplets themselves have been tested. They are functional, and we have done a small scale assembly at this point. You can see the picture of it on the bottom, and the whole wafer scale system assembly is still ongoing. It'll take some time, but that's where we are right now in this. So any questions?
Puneet, not specific to this, but there have been a couple of good questions in the chat. Maybe I can. First, this goes back to an earlier slide. What is the silicon overhead for multiple chiplets, and does your cost calculation take that into account?
So silicon, yes, the cost calculation in the beginning, it accounts for that, but it assumes that your IOs are more of kind of this style. The simpler IOs, these are not SerDes links and things like that. So the IO overhead is there, but it's not massive. There is an overhead of dicing as well, but hopefully not massive. And that's where also, again, small chiplets stop making sense cost-wise after a certain point, because those overheads start to add up. If you're going to make a 1 millimeter square chiplet where you have a 3 to 4 times size of the IO, then 100 micron dicing loss on the side, etc., it starts to add up very quickly. And that's also part of the reason why, at least we believe that cost point of view, only large SoCs broken up into small, not small, but moderate to large chiplets is where the sweet spot would be, probably.
Got it. Then the other question was, skew between differential NP lines can cause large current demands. Is this a problem, and if so, how is it avoided?
So there is no differential IOs in this. This is single-ended.
All our IOs. Okay. The next question was, a separate chiplet for IO, especially for analog IP. Do you see that as gaining traction over integrated SoC, given the challenge with analog scaling, margins, and testability?
It could for potentially off-package kind of connections. And I think the previous speaker and others have also talked about photonics as one instantiation of that. Where photonics is, from my point of view, is primarily an IO, right? Just a much higher speed IO, but it is an IO, and it does like other processes, not kind of the typical CMOS logic compatible processes. So yes, absolutely, but mostly for off-package type links where you want longer distance connections.
Got it. And then there's a very practical question: how did you implement the 20 nanofarad on-chip cap? Is it MIM, or are there any special materials? How much area does this?
There's no special materials. This is unfortunately we were stuck with whatever that process provided. There's absolutely no special materials. That's why that area is so large. I mean, 30% of a die area being just decap. I mean, you can imagine. I mean, how we hit it. So
yeah. And what's the speed of these IOs per line?
So they can run at up to 4 gigahertz, but we plan to run them at much lower, about few hundred megahertz.
What's the link length, the max distance they traverse?
So max distance is 100 micron interdie resistance plus, let's say, 100 micron buffer on each side, so about 300 microns.
Got it.
So the bulk of the cap is not there. The bulk of the cap is actually in ESD.
Yeah, I can imagine. And then last question, how did you test high-speed IO interconnects? Is there any way any DFT to test it?
So our high-speed I/O is not SerDes. I mean, that's what I keep emphasizing. These are simple cascaded buffer links. So these are buffers here, buffers there, and just like what you have on any modern digital SoC. That's it. All they need to drive is 300 microns of copper wiring plus some small amount of ESD cap.
Got it.
So testing this is definitely nowhere as close difficult to a serialized link.
Nice. Puneet, did you have more slides? Because there are other questions which I would have loved to ask, but I want.
Or we could stop here. This is the whole new section. So depending on if there's time, I would like to go through them. But if not, then we can just move on to the question.
Maybe what? Let's see. We have 4 minutes left. Maybe you could talk about pathfinding 2.5D substrates.
Okay. So I'll rush through this. And the point was with this exercise, what I wanted to lead into is that a general question that remains is there is a huge diversity in what the 2.5D integration technologies look like. Let's call it interposers look like. You could have diversity in what is the inter-die separation. You could have diversity in interconnect pitches, bump pitches, etc. And what we wanted to understand is at the system level, what matters. Because every time you make an iota of a change here, that's technology development. So understanding where it kind of buys you anything was what we felt was important. So we built a simple framework around it. I'm not going to the details of the framework, pathfinding framework, but let me show you some results. So first is the bump pitches. So the bump pitches, when you scale down the bump pitch, what that happens is effectively it allows you more IOs, or you can pack the same number of IOs in fewer quote unquote IO columns. So that reduces the total wire length that needs to, worst case wire length that needs to be driven. Okay. When I scale down the wire pitch, on the other hand, then if I keep the IO pitch constant, then what is effectively happening is to saturate the wiring density, I will need more and more columns of IOs. So that actually increases the wire density. Of course, it is increasing your bandwidth you can push out as well, but the latency of a single link increases if you want to hit peak utilization. Okay. So with this, what we figured is that scaling one alone doesn't buy you anything. You can keep on scaling IO bump pitches all the way you want, but you are not going to gain much unless you correspondingly scale the wire pitch or increase the number of wiring layers in the interposer at the same time. At least what we found is that scaling things below order about 16 micron bump pitch, roughly speaking, the benefits saturate very quickly. So the sweet spot is probably around 16 to 32 range of bump pitch, maybe a little bit lower depending on the precise application, but somewhere around there. And that is with about a 0.5 micron wire pitch. Now, ESD is a big deal. And it even becomes more important because the inter-die separation on these chiplet-based systems is much smaller. So as a result, ESD starts to account for a larger fraction of your load. And there also we looked at this, and essentially you can see here that depending on what level of protection is needed, it can start hitting both energy as well as bandwidth metrics by 20, 30, 40% type of numbers, just the ESD cap. So we have seen ranges all the way from 200 femtofarads ESD requirements to 20 femtofarads ESD requirements, depending on how the process is done. At least looking at our results, we believe that it needs to be below 50 or so, especially for these densely integrated chiplet type systems for ESD requirements.
So Puneet, 2 questions. If you go to that previous slide, maybe the one before. If I take a very, no, you had it 23.
Okay.
If I took a very, very high level view of power, what percentage of power is it in the transmitter, the receiver, as well as?
Very little.
Okay, very so total, if you had 1 picojoule, 0.1 picojoule per bit.
So I don't remember the precise numbers, but
percentages.
The transmitter and receiver are not taking up bulk of the power. Your wiring plus ESD load takes up a lot of power here.
I see. And if you break that up, ESD, is it more than the wiring? Or
that depends on the metrics, right? So if I assume that it's just 100 micron die separation plus, let's say, 50 to 50-ish micron of buffer for dicing on each side. So that's about 200 microns of wire. And how much ESD, if you need 200 femtofarads of ESD protection, that will be completely dominated by ESD. Wire will play no role in it. But if you're doing 20 femtofarads of ESD, yes, the wire starts to matter.
Okay. Last sort of a rapid round question. What's the intended end application of all this work? And what energy and performance gains are you expecting?
So for the wafer scale integration, our intended end application is what's graph analytics. So that's an emerging class of workloads where essentially in that workload, what you're primarily limited by is random access to a large chunk of memory. So conventional GPU, CPU tile systems, unfortunately, don't work well in that scenario. And that class of applications, I mean, like lots of them which fall into that bucket as well. And so wherever you are immensely limited by aggregate memory and bisection network bandwidth, that's where this wafer scale type integration, at least in our opinion, would work really, really well.
Perfect. Thank you very much. This was a very interesting talk. Thank you, Puneet.
I just want to highlight one more slide before I end.
Okay,
I know
no
I'm
problem.
going over time. Since we talked about chiplet ecosystems, I wanted to just highlight one small thing that when I designed chiplet interfaces, chiplet to chiplet interfaces, surprisingly, nobody talked about heterogeneous technologies sitting on either side. Because imagine a case where I have two 12 nanometer die connected to a chiplet interface, that chiplet interface could run at core voltage, 0.8 volts. Now, if I want to connect a 12 nanometer die to a 65 nanometer die, now the chiplet interface will have to run at 1.1 or 1.2 volts necessarily at the higher of the two. That has an energy overhead. Large, I mean, 0.8 to 1 volt is already about 30 to 40% energy overhead. And if this gap becomes even larger, if I want to push the die 2 to be 180 nanometer and die 1 to be 7, then their core voltage is almost a factor of 2 difference. And then you start worrying about even reliability issues on the advanced node die as well. So that's one more small thing to keep track of, that heterogeneity is nice, but you can't go too wild with it in these chiplet interfaces.
Fair. Sure. Thank you, Puneet. I appreciate this.
So once again, thank our sponsors, Advantest, Amcor, and Synopsys, who made this event possible. Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Amcor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.
Thank you.